It doesn't matter, but this is my coordinates in the web, so you can look me there. I'm going to speak. This is an introductory class. I will speak broadly, generally, about the complex system in the first part. Then I'm going to move to how to model complex systems, and I will start with two examples of modeling complex systems. The first one is about the standing ovation problem. I will present next, and if I have enough time, I will present the granometer model and how to model this. And if we are lucky, we are going a little bit in the math of how to do that. So, okay, I can do that. What is a complex system? Does Christina speak about complex system, how to differentiate a complex system from a merely complicated system? And complex system has two main properties. One is the emergence, in which we can see that the whole is greater than the sum of the part, but maybe sometimes the emergence is, it can be seen as, for example, synchronization, as Christina speak about. And the other is that there is no boss. In complex system, we have self-organization. And the system tends spontaneously to some level of organization. The cornerstone article in complex system is this of Phil Anderson, who speak about that if we know we have the ability to reduce everything to simply fundamental laws, does not imply that the ability that from those laws reconstruct the universe. I mean, we can know the fundamental laws, but how the particle assemble is a whole different problem. The behavior of, the behavior of complex aggregate system is a complex itself, and at each level of complexity, we have to do some fundamental research. I mean, when we have an assembly of different level of organization, we have always some complexity to do and some fundamental research in each level of this organization. This transparency is just to know that complexity is an inherent interdisciplinary concept, that new features emerge when we goes up and up in the level of organization, and the description of the entire system requires some theory that are not, we have to do these theories. Here are two examples of complexity. This one, if you know, let me see, sorry. This is a bunch of birds, are starlings, and this moves in a very coordinated and soft way, and we can do here how the behavior of the flock can be understood, and we cannot understand the behavior of the flock in terms of the behavior of each bird. The same happens in the brain. This is an fMRI data acquisition of some guy doing nothing, doing at rest, and we can see here that even when we are doing nothing, the brain has some level of organization. For instance, Starling flocks, Starling moving coordinate flocks, the flocks have the different sites has different or same movement patterns. Each bird only see those birds that are near to them, and even though there are some level of coordination at the scale of the whole flock. So how can it explain? Well, there is a very nice paper here that is a paper of Andrea Cabana and the people from La Sapienza, Giorgio Parisi, then last year Nobel Prize, when they study scale flicker relations and how to emerge and how to describe the statistic of this kind of flux. This is also related to the activity of the brain that writes in state, how when we are doing nothing, that appears region of the brain that move coordinately, and this is called the resting state networks. And this kind of organization rules the activity of the brain even when we are doing something, so it's very important to study this kind of organization. This is an emergent behavior. This is an emergent behavior in which group of neuron coordinates, and this produce behavior, produce perception, or produce every thing that we do with our brain. But here, sorry, I'm a little bit. We are focused on, and I will focus these classes in opinion formation process that, of course, can be seen as collective behavior because people interact with each other, and there are some process of agreement or interaction that can lead to collective behavior that they are important for our living. For example, process of agreeing, we have to agree to do something. For example, small groups in buildings, we have to agree to do something in the building, or we have to vote, we have to choose a president, and there are few options, and sometimes this process tends to polarization. People in group tend to change their mind. When they interact, people tend to change their interaction. The problem of opinion dynamics, opinion formation, has been approached by psychologists in the 50s doing experiments, and they start to uncover what are the main mechanisms on social influence and social interaction. Some of them Cristina mentioned in her talk as social pressure, imitation, adaptation to the environment, exchange of arguments, and we are going in the details in the class of tomorrow. Which are the common elements in complex systems? Well, in general, complex systems are composed by many units. There are no central authority, and as Cristina said, there are local nonlinear interaction. The nonlinearity is key here. The nonlinear interaction is key for producing emergent behavior. And the emergent behavior, of course, a consequence of those nonlinear interaction. So we have two scales at which we focus on complex system. One of them is the micro level, and when we uncover what are the local interaction among units, and the other is the global emergency in the macro level. There are plenty of examples. Here we have many of them. Pattern formation in which the units are matter, flux in which the units are birds or starling in this case, internet, Joule, cell in biological development, anthill, brain and cognition, social networks, etc. And in this framework, we can have agents. You can see here that I just reducing the problem some common elements. In some way, I'm thinking in modeling complex systems. Agent can be people, neurons, insects, molecules. The ensemble can be social group, brain, etc. And the emergent properties can have one of them, of these. So if we want to model complex systems, we can, for example, how a society behaves, or how or a group of ants, we have, a multitude of factors. We have many, many elements. So the first part to model a complex system is to simplify them, to simplify to the basic mechanism responsible for the emergent behavior. So we have to try to understand and try to formulate an idealized description of the reality that captures the emergent behavior we want to model. And we are used to that because we use that. We use, for instance, MAP. MAP is a model of spatial organization in which we simply don't take into account all the aspects of a given place, but the aspects that are relevant for example, go from one place to another. Yes, that is a model, a simplified model that are useful in our real life. So, three main features of complex system models. They are finite, although when we want to get some mathematical insight in them, we approach to infinite systems, but they are finite in size and in time. They are generally out of equilibrium. They're heterogeneous, and they have interactions. Yes? They are the main feature of complex systems. This is an example of a complex system that we would like to model. For instance, this is the first example I speak. I'm going to check the time. This is a standard innovation problem in which people are watching a performance and they finish, they upload, and they spontaneously start to stand and to give a higher ovation. So, if we want to model this, how we start? Can we model this problem? Well, I'm going to read this because it's although it's simple, the social dynamics responsible for this ovation is complex, okay? When the performance ends, the audience is what I tell before, they stand to clap, and then when one stand, others stand. So can we, in some way, reproduce the pattern of standing ovation, or just doing a simplification or get some approximation to this problem? Well, let's assume that we have n individuals, okay? Each one receives a signal that depends on the quality of the performance, see? This signal is Q. And let's call S sub I of Q as the signal received by each member of the audience. We could, here, we can go as complex as we want, giving some strange functional form for this function, but we start keeping the thing simple. So we are going to suppose that this signal is equal to Q, to the input received, plus some heterogeneity that is we given with a term of white noise with zero mean and some variance, okay? So this is the signal received. We have a large number of units. We have heterogeneity here. And now we have to solve the dynamics. So we start with a simple hypothesis that is each person has a threshold. Everybody has the same threshold. And when the signal is above this threshold, because this I get emotional with that, I stand and applaud. Okay? Okay. This is a very, very, very so simple model that we are missing a fundamental ingredient, that is interaction. Because if all people just behaves as the signal which receives, everyone, it's going to, everyone, the whole problem can be reduced to the problem of one person. So, sorry, let's add some parameter alpha, see, that give the percentage of people who must stand in order to ignore the initial signal and decide to stand up. So, our model is here. If the initial group of standing people exceed this threshold, then everyone stand and all the audience give a stand ovation. Otherwise, it remains in the initial groups that stand. Even if this is a simple model, of course, real ovation, we know, looking at these dynamics, that it's not going to be a good model. It's a very basic model. So, if we want to improve our model, we have to add some features, some relevant features. For instance, when the people go to an auditorium, usually they don't go alone. They go with other people, acquaintances, friends. And maybe they are more sensitive to the interaction with friends than with other people. If my friends stand and applaud, maybe I'm forced to also applaud. So I can take into account that I can go there with friends. Although in the previous model, there were not spatial organization. People can see everyone, but maybe the spatial organization is relevant because it's not the same, the interaction with people close to me that are in other part of the auditorium. So I can put some spatial structure, and also there can be location that may reflect preference of the performance, people that maybe are in some part of the auditorium. And I can also add that the interaction among people can have some weight that reflects this degree of heterogeneity in the interaction. And I can compare these two models. In the first model, the dynamics, it's going to be an initial decision to stand, followed with a second decision, based on how many people stood initially. And the social influence, everyone is equals, and I have at least 2 rounds of applause. But if I put these more ingredients in the model, I can have a richer model that can approach better to what we observe. So, which can be the research question from the stand innovation problem? Do performance that attracts more groups lead to more ovations? How does change in the design of the theater, for instance, by adding some balconies, can influence ovation? If you want to start an ovation, where you should place some shields, some people that start the ovations? Or if people are seated based on the preference for the performance, for instance, left or right side of the aisle, or more expensive seats or fronts, do you see different patterns of ovation? If I put some preference in the audience, can it affect the ovations? There are questions that I can ask in this problem. So I have a hands-on proposal for you. And if you want, those who are interested, the first one is implement the model 2 with spatial structure and location-based influence. The second one is add acquaintances influence. And the third one is, if you want, implement a version of some research question. Of course, we can take it nicely. If you are interested, we can do how to do that. We can do in the hands-on session. See? So this is the third proposal. I think that this slides is going to be available in the web. I don't know, but I can, you are writing there the question. I have another hands-on proposal, so I will move to another part. Here is when we want to describe or to model complex systems, we always have to reduce the problem. But how can I do that? How can I simplify the problem but keep the complexity? What means the necessary complexity to see the emergent behavior. How to model a complex systems? There are two basic ways, or more, but the first one is what I'm going to speak in the next lessons, using agent-based model. The other, as Christina said before, is use complex networks that we will see with Professor Semenchenko, with Vika over there. We can use also game theory, and Marcelo is going to speak about. If I use complex networks, I can use this for describe the backbone of the interaction, but also we can use complex network to describe emergent behavior, a functional network that also are going to see with you are going to see with Christina. When we perform agent-based model, basically our basic units are agents. These agents can be person, voter, institution, neurons, regions, etc. Each one of them will be defined by a state of a given dynamics. We are going to add interaction between or among agents, and we are going to study global emergent behavior. Our typical approach is to make assumptions about how they interact and try to study which is the emergent behavior that is a consequence of this interaction we propose. The first model, the second one, we are going to see in details, is the Granovetter model. The Granovetter model is a model that was proposed by Mark Granovetter, was a professor of sociology. In the 70s, in some stage of the sociology, they trying to, are you using the microphone or? Okay. When they try to study how is the behavior, the aggregate behavior of many people. Up to that moment, theories assume that the behavior of the group of people can be inferred of the behavior of the individual, or in the inverse, the behavior of the individual can be inferred from the behavior of the collective. And this behavior was based in norm, preference, motives, or beliefs, etc. What the approach of Mark Granovetter did was just focusing the interaction between agents, that the collective behavior of the group of people was driven by two basic features: interrelation, or interaction among people, and variability among individuals. And this is going to drive the system to collective behavior that are not aligned to the preference of the individuals. So the question Granovetter did is how to study collective Hola, sorry. Very. How to study collective behavior in situations where subject has two alternatives. I have to do something or not to do. I have to choose between two options. By my choice depends on how many people do these choices. For instance, in a riot, it says building a riot. Do I join a riot or not? This is the framework where Granovetter worked. And he proposed a model that is the basis of many other models that we are going to find in the literature of social systems that are the threshold models. See? The threshold model, each agent is characterized by a threshold. In this case, the threshold model in the Granovetter model represents the proportion of the groups he must see join to the riot before he going to join. For instance, I have a group of agents. Everyone has this number that represents a threshold. These people, this red one, have threshold 0. This is the leader. They don't need anyone to join the riot to start the riot. This is started, the leader. See? Then we have this other red one, that is this threshold is 1. So he needs or she needs at least one person starting the riot to join also to the riot. This has a threshold, the orange one has a threshold 8. It needs at least 8 people in the riot to also join the riot. Okay? So, we have that situation. We have a group of people that, for instance, that are walking around in a square, just very angry or something like that. And we have an instigator that engage a riot. For instance, take a stone and break a glass. So, it's going to start a riot or not? The question that Mark Granovetter did was, given an initial distribution of threshold, can we predict the outcome? The first sample we are going to see here is a uniform threshold distribution. Yes? So, and this is a very simple case. We have an agent with threshold 0, and another one with threshold 1, another one with threshold 2, etc. This is an instigator. And what happened is what is called the bandwagon effect. The green start the riot, the other one, the one with threshold 1, join to the riot. There are 2 people, the one with threshold 2, and so on, and we have a manifestation. Okay? All the people join the riot, and the proportion of people in the riot is all of them, is 1. Case 2, is stable, this solution. For instance, if this distribution is slightly perturbed, see? Yes, debería decir. Yes. We have almost a uniform threshold distribution, but we have the bad luck or the good luck that there are nobody in this square with threshold 1. Which happened? The instigator take a stone, start the riot, and there is nobody with threshold 1, so there are one with threshold 2 waiting for other people to join the riot, so nothing happened. These are crazy people. Nobody joined the riot. The equilibrium solution is 1 among n. So if we read the newspaper to the next day, we can see that a slightly variation between two initial conditions goes to two very different outcomes. Violent riot or just an unhappy customer. Okay? A chaotic. Okay. Can we theoretically approach this problem? Can we mathematically describe that? What Granovetter did in his paper was describe this in terms of the threshold distribution. I mean, how many people have a threshold X? And the relevant quantity here is the cumulated threshold distribution, because it tells us how many people has a threshold less or equal to X. So if we call R of t the fraction of individual joined to the riot at time t, then the evolution of the system is given by this simple relation, that the people that are going to engage at time t plus 1 is given by the amount of people that has a threshold equal or less than R. So it's f of R. If we plot, and of course the equilibrium situation is when the fraction of people at time t is the same that at time t plus 1. This is the stationary solution of this problem, and this problem can be solved in this diagram, in which here we plot the function identity, and here we plot the cumulated function. See? So if we start with a given number of rioters, a fraction of rioters at time t, R of t, the function, the cumulative threshold distribution, give us this outcome that is represent the number of rioters at time t plus 1, and this system is going to evolve until it reaches the equilibrium. If you use not a uniform distribution, but a truncate Gaussian distribution, between it has to be between 0 and 1, the threshold, it also looks something that Granovetter also notes, that is like this. This is the number of rioters as a function of the standard deviation of the initial distribution. And we can see here that it appears a critical value in which, of the variance, in which there is a huge change in the outcome. So it is real, it is describing something that is the amount of rioters is sensitive to some broader distribution, or maybe it's an artifact of this model that cannot solve well this kind of things. Well, this is a question we can do. And these are simulation of a Gaussian distribution, normal distribution from different variants. I can, for those of you that are interested in this model, I can share with you and collab, a Jupyter collab, that if you're interested, you can play with that, and you can add some aspects. So we can discuss later in the hands-on session. So this is a very nice model, because this is example show how two crowds, which in average are nearly identical, they produce entirely different results. And this is a problem that we have to deal with. And threshold model take the two elements of the collective behavior that are central to explain our research: heterogeneity of the preference and a nonlinear coupling between individuals. Hands-on, proposal 2. Can we do the Granovetter model with some kind of social structure? Can they add some weight in the interaction, some, etc. Friendships. Can we do another better model than this mean field model of Granovetter? Okay, if you're interested, we can do departing from the collab I'm going to share with you. I don't know, we are running out of time, so see, we have to finish at 11, no? At 11 was... Okay, I'm going to be faster in this final part. We can discuss later. Can we formalize the problem and to obtain a master equation, an equation for the dynamics of a threshold model? Yes. Well, we can do that. We can formulate a system of n agents in which each of them is described by a binary state. This binary state can be in state 1 or in state 0. In state 1, it means that the agent is engaged or interested of something else. In state 0, it's not engaged, it's not interested. And we are going to describe the system in terms of a macroscopic dynamic, a macroscopic parameter that is the fraction of interested people. And we have to add the interaction as Granovetter did, in which each agent can change his state from 0 to 1 if the fraction of interested people is above his threshold, or 0 if it below its threshold. Okay. I will finish here, but we can write a master equation. I mean, an equation which is a master equation? An equation can give us the evolution of the probability of having a fraction of interest in the system. That is going to be P sub k. P sub k, if we think a discrete problem, is k over n when we have k interested or engaged in our system. And we can construct this master equation with the gain terms and the loss terms. So we can go from cap minus 1 to the, or from k plus 1 to a state k, or we can go from the state k to k minus 1 or k plus 1. And we can write these transition probabilities, and we can perform the continuous approximation and just write down a master equation, and the master equation, the solution of the master equation is this differential equation, which stationary behavior here is the same that Granovetter found in the previous paper. Sorry about missing the details. You can follow this presentation. I also was skipping some part of the mathematics, but if you're interested, we can follow in the hands-on mode. So I'm going to finish here so we can enjoy some coffee and something to eat. See you in a while.